You ever try something new? Like a workout plan, a new study technique, maybe a diet, and you get to the end and you just wonder, did that actually do anything? It's a question we all ask. How do you measure real change and, separate it from just random luck? Well, let's get into it. Think about it. Let's say you're on a diet. You weigh yourself before, you weigh yourself after. And yeah, you see a change on the scale. But is that change really meaningful? Is it just, a daily fluctuation? Or is it a real solid result from all your hard work? Well, believe it or not, there is a powerful and actually kind of elegant tool designed for this exact kind of before and after question. And today, we're going to break it all down. So this tool is called the paired t-test. And you can think of it like a detective, really. Its whole job is to help us figure out if the change we're seeing in one group over time is, the real deal. Okay, so here's the official definition. The keywords you really got to pay attention to are related groups. This is not about comparing two different sets of people. No. It's about one group, measured twice. So your weight before the diet and your weight after, or your test scores before a new study program and your scores after. It's the same group, just at two different points in time. And honestly, this is what gives the paired t-test its superpowers. See, an independent t-test would compare two totally separate groups, like people who did the diet versus a different group of people who didn't. But the paired t-test, it measures the same people twice. And the advantage here is huge because it completely eliminates all those individual differences between people. We're not comparing you to your neighbor, we're just comparing you to, well, you. And that makes the test way more sensitive to spotting real change. But okay, before we can unleash this powerful detective, we've got to make sure our case actually follows the rules. There are a few key assumptions, a sort of checklist we need to go through to make sure our results are legit. So yeah, just think of it as a simple checklist. First up, the data has to be paired, a before and after score for the exact same person. Easy enough. Second, what you're measuring needs to be, well, measurable on a scale, like weight in pounds or a test score. Makes sense? And finally, here's a slightly more technical one. The differences between the before and after scores should roughly follow a bell curve. Now here's a really crucial part, how we frame the question. We basically set up two competing ideas, like a showdown. On one side, you have the skeptic's view, which we call the null hypothesis. This view just assumes nothing really happened, any difference you see is just random noise. Then on the other side, you have the hopeful view, or the alternative hypothesis. This is the idea that, hey, something did change. The entire point of the test is to see if we've got enough evidence to shut down that skeptic. Okay, theory is great and all, but let's see how this thing works in the real world. We're going to look at a pretty simple study that asked a fun question. Do summer holidays have any effect on the physical fitness of statistics students? All right, so here's our data. We've got 10 students. They all took a fitness test before summer break, and then the exact same 10 students took it again when they got back. And just looking at it, you can see, well, some scores went up, a few went down, some went up by a lot. It's kind of all over the place, a real mixed bag. Okay, so let's zoom out and look at the big picture. When we average all those scores, it looks like, hey, fitness actually went up a bit. The average score went from 46.4 before the break to 49.7 after. Now, at first glance, you might be tempted to say, awesome, summer break is great for fitness. But we're not going to jump to conclusions, right? We're smarter than that. In this right here is the million-dollar question. Is that little 3.3-point difference a real, genuine effect of summer break? Or is it just statistical noise? Could we have gotten a result like this just by pure chance? This is exactly what our detective, the paired t-test, is built for. All right, the moment of truth. We've run the numbers. The detective has investigated all the evidence. So let's see the final report. What did it find? And here it is, this one number. This is the single most important piece of information from our test. It's called the p-value. And what this number tells us, in a nutshell, is the probability of seeing these results if the skeptic was right all along, if nothing actually changed. So what does a p-value of 0.197 actually mean? Well, the standard cutoff in science is usually 0.05. Our number, 0.197, is way bigger than 0.05. So what does that tell us? It means there's almost a 20% chance that this difference we saw happened just by random luck. And since that's a pretty high chance, we have to say the result is not statistically significant. So let's break down that final verdict. In fancy stat speak, we'd say we do not reject the null hypothesis. But in plain English, it means the skeptic wins this round. Even though that average score did go up a little, the change just wasn't strong enough or consistent enough for us to say with any confidence that the summer break caused it. Bottom line, we just don't have the proof. And that's really the big takeaway here. The paired t-test is such an incredibly useful tool because it stops us from jumping to conclusions. It gives us a solid, reliable way to figure out if a before and after change is a real thing or just a random fluke.
And that, of course, brings it all back to you. I mean, think about it. From a new productivity app to a different morning routine, we are always making changes and hoping for the best. This test gives us a way to think critically about those changes. So I'll leave you with this. What's the next before and after question in your life that's just waiting for an answer?